afternoon and welcome to our live stream of Tour of the Universe. My name is Ryan White. I'm the Senior Director of Morrison Planetarium and Science Visualization at the California Academy of Sciences, and I'm going to be your host for the next half hour or so as we travel from in orbit around Earth out to the most distant light we detect from the universe around us. This is a program that we normally live stream and sort of simulcast from Morrison Planetarium, but for December and January, we're doing something a little bit different, and I'm actually here in kind of the bowels of the Academy in a room underneath the planetarium, and I'll be piloting around a virtual model of the universe, and it's a model of the universe that's built in a piece of software called OpenSpace. It's an open source piece of software that you can download. We'll be sharing links in the chat. And as long as you're paying attention to chat, you can also pose questions there. Since this isn't just a simulcast, I'll actually be able to answer questions as they come up. So feel free to put them in chat and we'll share some of those if they come up. And otherwise, I will be piloting you, as I said, from in orbit around Earth, where we're starting here with the International Space Station, out to the farthest reaches of the universe. So with that, let me go ahead and take myself off the screen, if that's okay, because really I want you to be paying attention to the visuals that we're looking at here now as a full screen. If you've been watching for a couple minutes, you've noticed that our International Space Station has kind of traveled from day to night, which is not exactly where it is right now because I wanted to choose something with a little bit of drama. But you can see city lights underneath the ISS as we pull backward from it. And I'll just note that this is as far as humans travel physically out into space these days. A few hundred kilometers, a few hundred miles above Earth's surface. People have traveled a lot farther out into space, but we are going to voyage through a virtual model of the universe, which will allow us to break the speed of light, which will allow us to travel much, much farther than any astronauts have ever traveled. So it looks like the ISS is kind of plummeting into Earth. That's actually not what's happening. We're actually just pulling away from Earth's surface and the International Space Station. So let me kind of accelerate. And the line that I brought up is actually the trajectory of the ISS, the International Space Station, in its orbit around Earth. And now, if you're pretty good at geography, you might be able to recognize that we're actually looking at the ISS over North America, in fact, over the northern U.S. And you'll notice something interesting here on the kind of left-hand side of the screen. This is about the right time of day. We're moving from, of course, daytime into night as Earth rotates. We here in San Francisco will experience nighttime and darkness in just a few hours. But I want you to call your attention to this kind of structure here and also the kind of limits that you see on the data here. Basically, this is a good illustration of the data that we use to fuel OpenSpace. We're using real data, so you'll notice that this kind of image is kind of cut off here as you get too far north, and that's because these are actual images from NOAA satellites using an instrument called VIIRS, which makes observations in the visible and infrared parts of the spectrum. And the instrument only covers a certain, up to a certain latitude, so you don't see data up here because it kind of cuts off. But this is data from just yesterday, the most recent covering this part of the globe. And for those of us here in Northern California who are experiencing lots of rain, you can see that atmospheric river, the remarkable atmospheric structure that's dumping so much water and snow on California right now. And that's because this is very current data. This is just from yesterday. And although our main focus on the show today is going to be about space, I just wanted to call attention to that aspect of our representation of Earth. Because this is a data-fueled representation of the universe around us, including our home planet. And although our focus is going to be on astronomical objects, Earth is, of course, an important part of the stories that we tell here at the Academy, and so it's worth kind of pointing that out before we get too far out into space. So let me go ahead and actually show you some distance markers that I'll be making references to throughout the presentation. And to do that, I'm going to add, again, some more lines, kind of like the line that I showed that revealed the trajectory of the International Space Station. These are revealing the trajectories, the orbits of natural objects in our solar system. We, of course, have left Earth behind, and as we can see kind of peeking up from the lower right-hand side of our image here, we have the orbits of the other planets around the Sun. And around Earth, we have this orbit of the Moon. Now, I won't actually spend a lot of time visiting the Moon, but I do want to point out the diameter of this is about 800,000 kilometers, about a little less than 500,000 miles. And if you look at this distance between Earth and the Moon, I want to call your attention to that because that's as far as humans have ever traveled into space. I mentioned that the farthest anyone is going right now is in low Earth orbit, a few hundred kilometers above Earth's surface. But once upon a time, back in the 60s and 70s, about a dozen lucky Americans got to make this trip from Earth to the Moon. It took about 3.5, 4 days. But they traversed the entire 240,000 miles, 400,000 kilometers in that period of time. The farthest humans have traveled out into space. But what I want to mention is a way that I'm going to refer to distances as we get farther and farther from home. And that is in terms of light travel time. Light travels at a constant velocity in the vacuum of space, about 186,000 miles per second, or about 300,000 kilometers per second. And so it traverses that distance between Earth and the Moon in about a second and a half. So when you look at a moon in the sky, and we did have a couple clear nights here where you can see a nice crescent moon in the evening sky, you're seeing light reflected off the surface of the moon. It's taken about a second and a half to travel to see to our eyes on Earth. Now, if you think about that, that's kind of about the length of a brief pause in conversation, a second and a half. But we're going to talk about distances that are much, much greater than the distance between Earth and the Moon. So let's take the Sun, for example. Here we have the orbits of the terrestrial planets. We got Mercury, closest to the Sun, part of Venus's orbit, visible here, Earth, the third rock from the Sun, and Mars. Now, Earth is about 150 million kilometers from the Sun, about 93 million miles. And if you think about that in terms of light travel time, that's about 8.5 minutes of light travel time. So we can refer to the Sun being 8.5 light minutes away. And if you think about how long you might spend doing something that would take 8.5 minutes, maybe that's, I don't know, a really quick lunch, something that you would eat in a hurry on your way someplace. That's maybe 8.5 minutes, a quick meal between maybe in a busy schedule during the day. Now, as we travel farther from Earth, we'll see the orbits of the other planets, the other 4 planets, not the terrestrial planets, but the giant planets. We have Jupiter, Saturn, Uranus, and Neptune. Now, to get a sense of scale for the entire solar system, at least as measured by the diameter of Neptune's orbit, Neptune's orbit is a little less than 8 light hours across. So it takes light a little less than 8 hours to go from one side of Neptune's orbit to the other. So if you think of the diameter of the solar system as measured by Neptune's orbit, I mean, there's other stuff out there, but Neptune, the most distant planet, it's about 8 light hours. So if you think of that, that's maybe a good night's sleep. But what's going to become really challenging here is that the distances to other astronomical objects are much, much greater. The nearest star is about 4 light years away. And so when we look at these other objects in the universe around us, we're seeing light that has traveled over a period of years or even decades or centuries or longer to reach our telescopes or observatories on Earth. And when you look at the nearest star, we can't see it in our field of view right now, you're seeing light that began its journey more than 4 years ago. If you think about that, like the 8 hours that it takes light to cross our solar system, maybe that's a good night's sleep. 4 years, that's more like a high school or college education, which may or may not have many good nights of sleep. But these distances become really mind-boggling really fast. To put a bit of a human imprint on this, let me go ahead and add some more trajectories, some more lines. And in this case, these are the trajectories of the 5 fastest spacecraft that have been launched into the universe around us. Now, these were all spacecraft that were designed to explore parts of the solar system. So their main objective was not to become interstellar travelers, but that's essentially what they have become. They're traveling fast enough to escape the sun's gravitational influence. They're traveling basically at the escape velocity of our solar system. And 4 of these were launched back in the 70s. And I think I'll get this right. This is the Pioneer 10, and I think Pioneer 11, and then Voyagers 1 and 2. These trajectories are the spacecraft that were sent out to explore our solar system in the late 70s. And so they've been traveling almost 50 years away from our home planet Earth. The 5th one is a little spacecraft called New Horizons. That explicitly went on a high-speed mission out to Pluto, and that was launched in the early aughts. But if you look at this kind of representation of the fastest spacecraft, the fastest like nuts and bolts objects we've ever built, this gives you a sense of how far we've journeyed into the universe around us. And since you know that the diameter of Neptune's orbit is about 8 light hours, you can see that none of these spacecraft have traveled as far as light travels in a single day, even though some of them have been traveling all of them have been traveling for decades, some of them for nearly 50 years. So again, the scale of the universe around us is sort of mind-numbingly, mind-bogglingly huge. To continue our journey away from our solar system, we're going to keep pulling away from Earth. We're going to allow the sun to be brightened to its appropriate brightness. We kind of made it extra dim inside the solar system. And now we're showing the brightness of the sun correctly compared to the brightness of other stars in the the galaxy around us. So we've rapidly traveled much, much faster than the speed of light, and sorry, I just saw this quick question. Is the New Horizons spacecraft traveling faster than Voyagers 1 and 2? I am 99% sure that the answer is yes. I actually should check that to make sure. But because it was actually launched at a higher initial velocity and it basically sped directly out to Pluto, it had a greater initial velocity than the Voyagers did initially. And the Voyagers have been slowed down by the gravitational pull of the sun. They have escape velocity. Eventually they will escape the sun's gravitational pull, but they're still being slowed down by the sun's gravity. So to feel perfectly secure, I would say that I would probably ought to Google that, but I think that New Horizons is indeed traveling faster than the Voyagers. So as we pull farther away from our sun's location now, what we're seeing is our sun relative to other stars in our galaxy, the thousands of stars that are relatively close to home. And we're kind of continuing to drift around the sun. So what we're seeing is this kind of illusion of 3 dimensions. It's not really an illusion because the data are accurate. Each of these stars is represented in its best known distance from our star, the sun. But you'll notice that star is kind of it's an average to sort of dim-ish star. There are other stars that are brighter. We kind of exaggerated the kind of brightness of these stars by giving them big halos, but you can see that several stars that are relatively close to home are actually much brighter than our sun. As we continue to pull away, we'll see more and more of these stars in our relatively nearby neighborhood of our galaxy. I'll introduce our galaxy in a moment, but before I get too far from home, I do want to point out that, of course, we now know that many of these stars have planets in orbit around them. So if we wanted to highlight all of the stars that have planets in orbit around them. Some of these may have more than one planet, but each circle kind of designates the location of a star with a planet in orbit around it. And this doesn't represent the orbits. The orbits would be tiny, and they would be kind of drowned in the brightness of the star, even just the way we're representing it. But so smaller than a pixel or so. But these circles just are locators to mark where we know of planets in orbit around stars. And so each one of these represents the location of the star. And you'll notice that what we've done is we've drawn them a consistent size. And so ones that appear smaller on the screen are actually farther away. So you can get a sense of our nearby stars and how many of them have planets in orbit around them. And these are only the planets that we know of. Making statistical arguments, we can say that there are many, many more that we haven't found yet. But finding planets is tricky, and it takes numerous observations to really pin down not just the presence of the planet or not, but also the size, the orbital period, things like that, things that are intrinsically interesting to know about these planets in orbit around other stars. And of course, the really compelling question is, as we kind of look at more of the sky, I'll point out one feature in this data set in a moment, but one of the things that's really compelling as we think about planets in orbit around other stars is that there might be, I mean, certainly we don't think of life existing on stars, but planets. We've all probably watched Star Trek or something like that, or can imagine that life could exist on planets around other stars. It's inspired science fiction for decades. So if we're going to look for other life in the universe, these are kind of the starting points. But let's flip it around for a moment. If we look, the most common way for us to look for life, intelligent life at least, around other stars, is to look for radio signals. And there are all kinds of reasons for that. We invented radio at an early enough stage that maybe maybe we're just looking for what we would think of ourselves as transmitting and being able to detect. But radio signals are a form of light. They travel at the speed of light, and we can represent the outer limits of the radio signals that have expanded away from Earth by this sphere. We're starting out inside the sphere, but as I pull away from Earth's location even farther, you'll see this is a sphere centered on our sun, on Earth. And if you can imagine, it's not every radio signal that escapes Earth's ionosphere, but television carrier waves, actually atomic explosions and radar, all of these technological phenomena create radio emissions that can escape our ionosphere and could sort of fill up this volume of space. And what that means is that if we're imagining an alien civilization that could look back on Earth and detect our radio signals, then it's really only these relatively few planets inside the radiosphere that could look back at Earth and potentially detect our technosignature, our technological signature of our radio waves. Simply because we only started transmitting back in the very late 30s, early 40s. The radio signals haven't had time to reach planets, for example, out here. Or, as you can see, and as I mentioned before, the size of the circles represents their distance, so you can see this large collection of exoplanet markers is off in the distance. We'll get a different look at that in a moment. That's data from the Kepler mission, which identified thousands upon thousands of extrasolar planets, of planets around other stars. But of these thousands of stars, only a relatively small number, the ones that are inside our radiosphere, could potentially detect a radio signal from Earth. The others are simply too far away. Now, eventually, this sphere will expand. I mean, it's about 80 some odd light years in radius now. And as it expands, it will wash over more and more planets, but the signal also grows weaker over time. So It's a challenge to think about how other civilizations could even look back at Earth and detect our presence, at least in the form of radio waves. There are probably other ways. It's a whole nother conversation to be had. But this radiosphere, as we call it, kind of represents our electromagnetic footprint out in the universe. So if those trajectories of the fastest spacecraft we built represent our nuts and bolts movement out into the universe around us, this represents our electromagnetic footprint. This is as far as our sort of technology has traveled in the form of light emitted by our technology. So as we pull farther and farther from home, the sphere is going to get smaller and smaller. And if we think about this as kind of a technological history of our species relative to the size of the universe, we begin to think of, remember those initial comparisons of the second and a half of light travel time from Earth to the moon at 8.5 minutes, from the sun to Earth, 8 hours across our solar system, 4 years to our nearest star. Now we're talking about, those are all kind of human timescales that maybe we've all experienced, but now we're talking about the kind of history of our technology on our planet. And as we pull farther away, we're going to be confronted with even greater and greater distances. And what I like about the radiosphere is that it remains visible even as we pull far enough away to reveal the structure of our galaxy. I made reference to our galaxy earlier. I talked about the stars, the sort of neighboring stars in our galaxy. And for the moment, I want you to ignore these kind of red blobs that appeared in the background. We'll get to those in a moment. But this is our galaxy, our collection of hundreds of billions of stars. And the stars that we see in our night sky are just a small, small fraction of the total number of stars in our Milky Way galaxy. And the size of our galaxy is truly mind-boggling, because the diameter of our galaxy is about 100,000 light years. So our nearest star, 4 light years away, high school or college education. 100,000 years, that's more akin to the age of our species. It's about the time when our species was leaving Africa for the first time. And the size of the galaxy is sort of mind-boggling in that respect. Now, I do want to, again, call attention to the radiosphere. That's our technological footprint in the galaxy around us, and it gives you a sense of scale for humanity's technological innovation versus the period of our entire species history on the planet. And now to call your attention once again to those little blobs in the background. So far, the points that I've called your attention to are sort of the orbits of the planets, locations of stars that have planets in orbit around them. Now, looking at our galaxy, this is our collection of hundreds of billions of stars, our Milky Way galaxy, again, about 100,000 light years across. You can see 2 satellite galaxies, the Large and Small Magellanic Clouds. They actually orbit our own galaxy. But all of these little circles, these dots in the background, actually represent entirely other galaxies. Each one perhaps as large, some even larger, than our own Milky Way galaxy. So now what we're seeing is what we can begin to call the large-scale structure of the universe, the collection of galaxies in our universe. And this is where the distances get even kind of more mind-boggling. Before we get too far away, I do want to call your attention as we pull away from our Milky Way galaxy, as well as the Large and Small Magellanic Clouds kind of following along, that we reside in a cluster, not really a cluster, a small group of galaxies. In fact, we call it the local group of galaxies, 40 or 50 galaxies. But in fact, that's not a particularly impressive number of galaxies. Instead, galaxies do tend to clump and cluster together. You can see these regions where there are many, many galaxies all kind of clumped together, and then areas where there are not many galaxies. And for example, this area here on the lower part of the screen is the Virgo supercluster. That is a collection of about 1,000 some odd galaxies, a much denser conglomeration of galaxies than our own local group. And now, as we continued our pulling back, we're fading up more and more of these points representing individual galaxies. They're color-coded by the relative density of galaxies, so the regions where there are more galaxies are color-coded kind of that orangey hue, whereas the others are the kind of more aqua color. And you'll notice, and I feel compelled to note, that there are what we call artifacts in the data. First of all, you'll notice that there are not many galaxies sort of over here on the left or over here on the right. And it's not because there are no galaxies there, it's just that we haven't surveyed that part of the sky, or haven't completed surveys of that part of the sky. So where you see all of these galaxies is where we've surveyed the universe around us, making very careful measurements to determine the distances to these individual galaxies. But also, you'll notice that they all kind of seem to point back home, which is a little deceptive, because part of the way we make the measurement of the distance gives essentially an error, meaning we know its distance sort of plus or minus a certain range. And when you include that error, you end up with these sort of giant fingers pointing back toward our location here in the center of the data set. But that's not real. That's just because of the way we're making the measurement of the distance. And again, these regions where we don't see many galaxies, it's not real. It's just that that's where we haven't yet mapped the universe around us. So if this were a 17th century map of the ocean, there'd be sea monsters and dragons here. Instead, we've just left that space empty. And now, what I'd like to do, finally, is sort of really come back to this punchline of light travel time that I introduced very early on. So I talked about light travel time of 1.5 seconds from Earth to the Moon, 8.5 minutes from the Sun to Earth, 8 hours across Neptune's orbit, 4 years to the nearest star, 100,000 light years across our galaxy. Now, we've traveled in just a few minutes a distance that light would actually require millions, in fact billions of years to traverse. And the punchline to all of this is what I'll kind of fade up here in the background as we pull very far away from our home in the center of all this. And more about that in a moment. And that is what we call the cosmic microwave background. This is not a map of, or an image like the image of the clouds that we saw earlier in the show. This is kind of like a heat map in the sense that this is a measurement of microwave radiation that is coded by regions that are hotter or cooler. So we have lots of galaxies kind of in the way here at the moment. Let me pull that a little farther. But if you look at this mottled pattern of the cosmic microwave background, the bright parts are hot regions in this cosmic microwave background, and the dark parts are relatively cool regions. And this is actually the oldest light that we can observe, not because of any limitation on our telescopes, but because before this light was emitted, the universe was too hot and dense for light to travel very far. So it was at a point when the universe cooled down and this light was sort of free to travel, in fact, travel for billions of years to be detected by the Planck telescope, which made the measurements that we used to create this map. And so this earliest light in the universe has embedded within it a sort of fingerprint of the structure of the universe at the time. Those hot parts, the bright ones, correspond to regions that are maybe not quite as dense as other parts. The dark parts correspond to very dense regions of gas in that early universe. Those dense regions collapsed to form the clusters and superclusters of galaxies that we see around us. And the hotter portions are the regions where we don't see as many galaxies today. And so we actually see this baby picture of the universe in the cosmic microwave background. So finally, I want to take us all back home, but I also want to mention one thing that I kind of mentioned in passing. I referred to us as being at the center of this image, this three-dimensional virtual model of the universe. But that shouldn't be interpreted as us being at the center of the universe itself. The universe doesn't have a center. We end up at the center of this image in the sort of here and now. And this is a three-dimensional image, but it's really in space and time, the distance of the objects away from us. And because light travels at a finite speed, it's fast, but it's not infinitely fast. Because it travels at 300,000 kilometers per second, 186,000 miles per second, it means that looking out into space is looking back into time. So when we look at galaxies far away, we're seeing galaxies that are kind of at a younger age in their development, and we look at the cosmic microwave background, we're seeing this baby picture of the universe. So that light travel time that we used as a yardstick actually ends up having this punchline of revealing to us the entire history of the universe in this sort of three-dimensional model. So it's not that we are at the center of the universe, rather it's just because we're the ones drawing the picture. And to do it consistently, we end up at the middle of all of this. So with that, let me go ahead and take us on home. We'll fly past the galaxies in this collection of data that's been accumulated over years with different surveys, through the myriad galaxies that are relatively close to home, back to our own Milky Way galaxy. And I left the radiosphere up so we can get this as a sense of scale, but as we go ahead and approach home, let's go ahead and turn it off. Back through the stars that are relatively close to home, many of which, as we know well, have planets in orbit around them, and back to our own parent star, the Sun. We'll once again see the orbits of our planets in orbit around the Sun as we fade the Sun to be a more reasonable brightness at the center of our model. And then we'll approach our own home, the third rock from the Sun, our own planet Earth. So I want to thank you for joining us on this quick tour of the universe today, from the International Space Station out to the cosmic microwave background. If you have a chance to see this in Morrison Planetarium, it's far more impressive than watching it online. And if you can't join us in the planetarium, please feel free to join us every Wednesday at 4:30, when I and other people will host our tour of the universe to take you on a similar trip. Thanks for joining us, and I hope you have a very happy New Year.